In order to produce quality parts, we need to understand measuring principles. For many of you, the decimal system may be a piece of cake. For those of you that viewed our course on how to run a lathe, the decimal system should be firmly etched in your brain. But for those of you that got up late or missed math class, let's take a refresher course and go over the decimal system so measuring and producing quality parts will be a little bit easier. All right, we have what we call a Texas inch here, and we're going to break that down into a decimal system. We'll start at 0, and from 0 to 1 inch, if we were going to divide that into the decimal system, we would have 1,000 parts. We're going to take and very finely divide that inch up into 1,000 pieces. If we go to a half inch, how many thousandths are in a half inch? You guessed it, 500. So the decimal equivalent of a half inch would be 0.500 or 500 thousandths. In a quarter inch, simply half of that, 0.250. Are you getting the hang of it? I hope so. It's really pretty simple. An eighth of an inch, again, half of a quarter, 0.125. A 16th, 0.0625, and a 32nd of an inch, 0.031. Okay, so that pretty well breaks down that inch into 32nds, 16ths, 1/8, quarters. 3/8 would be, think quickly now, 0.375, 3/8 of an inch. 5/8, we're simply adding 1/8 to a half. So we've got 0.625, add another eighth to 3/4, 0.750, and one more eighth to 7/8 at 0.875. So by fully understanding the decimal system, we can take very precise measurements. Now there's a variety of tools out there that enable us, accompanied with our knowledge of the decimal system, to measure precisely. And by far the most popular is the dial caliper. Now many years ago, before we actually had a dial caliper, we had what was called a pair of verniers. Okay, and this is a 9-inch pair made by the folks at Starrett. And you can see closely, we'll give you a zoom in on the 1-inch scale here. And you can see where we've broken an inch down into hundredths. We have 1/10 of an inch, 2/10, 3/10, all the way to 1 inch. Now between the 0 and the 1, we have 4 additional graduations, and those are for 25 thousandths. So we have 25 thousandths, 50, 75, and 100 thousandths. And using the vernier scale that we see here, we've also got 25 graduations across the bottom. So if we were to close this up when the 0 was exactly on top of the 2, our gap is now, or our measurement is 200 thousandths. As we index that farther apart, we're going to need to be reading on that vernier scale. We would look across the lower end of the scale until we found which graduation lined up. And if we look closely now, the 20 and the 7 line up exactly. So we would have 220 thousandths. Okay, takes a good pair of spectacles. For those of you that are losing your eyesight, grab those reading glasses, allowing you to read that vernier scale a little bit better. Okay, so let's take a look now at a more modern pair that many of you are familiar with, called a dial caliper. The invention of the dial caliper really revolutionized the measuring world in terms of allowing the average bonehead to measure precisely. Once he understood that each revolution of the dial was 100 thousandths, he pretty well grasped the idea of the decimal system. We've opened the dial calipers, and you can see they have graduations in 1/10 of an inch or 1/100th graduations across the base of the dial. So there is 100 thousandths when our needle is lined up and we see the exposed 1. If we want to go to 1/8 of an inch, whose decimal equivalent is 125 thousandths, we can see we've passed the 100 thousandths graduation mark. We have 25 thousandths rotation on the dial, so we had 1/8 of an inch. 150 thousandths up to the next graduation at 200 thousandths. And this will carry all the way through the line from 1 inch, 100 thousandths, 1 inch and 1/8. Close them up a little bit. There we go. It's important that we make sure the line is either exposed or not. Okay? A lot of people would mistake that who are not familiar with it. They would see the 1 and see on a 90 and they'd go, well, oh, that's 1 inch, 190 thousandths. Not really. We haven't fully exposed the graduation on the inside face of our dial caliper. So don't make that mistake and then find out later that you've machined too much off, okay? Take your time, play with a set of dial calipers where you fully understand it, have somebody practice the decimal system with you and set those dial calipers at that decimal equivalent. Buy a good pair of dial calipers when you purchase them. You'll see a lot of dial calipers are made overseas and they're pretty cheesy. Buy a good pair from Starrett, Mitutoyo, Brown & Sharp. With proper care, they'll last you a lifetime. Now let's measure a couple of parts with the dial caliper and we'll see how versatile it is. It not only measures outside diameters, but inside diameters as well as depths of holes, and I'll show you that when we start measuring on our tooling block. We've got a piece of aluminum here that we've machined, and we've got several measurements that we need to take. Let's measure the thickness now. Hold our part, and you want to press gently on the dials when you close them. We don't want to scrounge down. We want consistent, accurate readings. And in order to get a consistent, accurate reading, the closure pressure must be consistent. If we're to push really hard, we can vary the thickness of this part as much as 1/1000ths to 1/1000 and a half. So we've got 985 thousandths is the thickness of this particular part. Let's go ahead and take a width dimension now and see what we have there. Okay, we've got 2 inches, 974 thousandths is the width of the part. We've bored a couple of holes or counterbored a couple of holes. Let's check those diameters. By doing so, we're going to be using these inside contact points on the dial caliper. You can see as we close it that those two intersect one another when we zero out. So we can measure pretty precise the inside diameter of a hole. And this particular hole is 625 thousandths in diameter. Another advantage of the dial calipers is the little tail that sticks out of the back of the caliper. We can use this as a depth mic as well. It's not as precise as an actual depth mic, but in most cases close enough for general machine work. We would simply set the part or set the dial caliper on. I like to stick the depth mic tail out a little bit farther and then push the caliper down until I come in contact with the base material. At that point, remove the caliper and take a reading. And our hole depth is 151 thousandths for the depth of that particular hole. Now let's measure the internal width of this slot. Again, we're going to use the inside contact points, and that measures exactly 375 thousandths. Let's check the depth of the T-slot that we've machined. Again, we're going to extend our tail out a little bit deeper, push the caliper down until we just come in contact with the surface and take our reading. And we're 313 thousandths in depth. So you can see the versatility. It's well worth your time to spend the extra money and get a good set of dial calipers. Now, if we want to machine really precise parts, we need to have a good 1-inch, 2-inch, 3-inch micrometer, depending upon the type and size of parts that we're going to machine. A micrometer of this type with a 1/10 indicator allows us to break the inch down into 10,000ths of an inch. So we've just showed you with the decimal system now of breaking an inch down into 1,000 pieces. Close your eyes and visualize breaking that same inch down into 10,000 equal parts. Pretty fine graduations. In order to use a micrometer and read the 10th scale, Just like we used and showed you in the example with the veneers, we've got a scale across the top, or a veneer scale, that we are going to read in order to break that thousandths down into 10,000ths of an inch graduations. With the micrometer closed, okay, and while we're closing a micrometer, we've got a little click adjuster here to give us very consistent tension when closing the mic. Remember, we told you earlier when working with a pair of dial calipers that we want to have consistent closing pressure on the dial calipers, ensuring a consistent reading. That's what our click stop is for on the back of the thimble on the micrometer. As we close it up, we can simply go 2 or 3 clicks, and this gives us a consistent torque setting, if you will, in closing the mic. So when the micrometer zeroes out, for each revolution of the thimble equates to 25 thousandths. So if we expand that out, we can see the little 25 thousandths graduation on the veneer scale. So keep that in mind as we rotate the thimble on around. Okay, there's 100 thousandths. If we're to zero out at that point, the distance between our little carbide anvil there is 100 thousandths. To go to 125 thousandths, we'd simply come back to 100 thousandths plus 1 graduation and line up at 0. Our next graduation is 1, indicating 1,000ths of an inch. But we're not quite to 1,000ths of an inch in this particular setting. We're approximately halfway between the 0 and the 1. So in order to get an accurate reading, we simply invert the micrometer in this fashion, and again, look for which mark lines up with the opposing mark on the thimble. In looking closely, we can see that the 6 lines up with the graduation directly across from us. This tells us that we have 6 10,000ths of an inch. So if we go back to our scale now and we're ready to read and write that dimension down, carrying it over to the next decimal place, we would have 0.1256. This is the 6 10,000ths that we've picked up on the scale on top of our mic. So this allows us very precise measuring. And any time that you're measuring in tenths, it's very important that we keep the anvil surfaces of the micrometer, the dial caliper, the depth mic that we're using free from any grit or debris. Just the slightest little bit of grit or lint in between those anvils can affect the measurement, this 10,000ths of an inch that we're looking at. You can wipe them off with a Q-tip and some acetone is a real good way to protect those. When you store your micrometer or put it away in the toolbox, never close it up tight. The micrometer is not a C-clamp. It is a precise measuring tool, and we want to protect it. So we don't want to be junking the tool by sending it over to the welding department. The proper way to hold the micrometer for measuring is this way. We're going to take this finger and it goes between the saddle. We rotate the thimble with our index finger and our thumb. Okay? This is a way if we're going to measure a part, and I'll give you an example. Let's measure the stem from the depth mic. Okay, we're simply going to open it up, turn it and close it. Now in this position, if we want that same repeatability, we're just going to open, click our ratchet stop 3 times, and take our reading. And we've got 157, and let's see how many tenths. About 4 tenths is the diameter of this depth mic insert. Okay, now let's take a look at a depth mic while we're on that subject. The depth mic is a very precise tool for measuring the depth of a hole or counterbore that we've machined. This is a digital made by the folks at Mitutoyo, kind of goof proof. For those of you that haven't really grasped the art of measuring yet, you can get yourself a digital caliper, digital depth mic, digital micrometer till you get the hang of it. Alright, same thing applies. We just turn the thimble until it bottoms out in the hole. And again, you have to have a feel at this point. You simply don't crank it up with lots of horsepower, because watch what happens. We'll give you a close-up view here on the contact shelves. If we continue to crank it up, what's happening? See, we're bottoming out and we're lifting the base of the depth mic up, and we can't get an accurate reading by doing so. We hold it firmly down on the plate, then we simply tighten it up, use our ratchet stop on the top, click it over, and we can get an accurate reading of 150 thousandths. It's the depth of that hole. You've got your interchangeable rods. The rod that we're displaying now is the 0 to 1 inch rod. The second rod that I'm holding in my hand is from 1 to 2 inches. So depth mics will come with different length of rods depending upon the different depths of holes that you'll need to measure. All right, that pretty well covers the measuring tools to cover most of the things you're going to be dealing with on the milling machine. If you have any questions, consult your textbooks or our course on the lathe. We deal with different measuring tools there as well. All right, I'm getting tired of the book work and the measuring. I'm about ready to start making some chips. How about you?